My name's Jacob. I work at Cray as a performance engineer. I work specifically on like scalability of machine learning and deep learning applications. And I'm going to talk to you about sharing resources with applications that are doing distributed deep learning. So what I'm going to talk about is I'm going to introduce the idea first off of network congestion. So essentially making the argument that network congestion is something that everybody is actually already really familiar with, and sort of provide a overview of how deep learning can make it worse, and what are the options for fixing it. So the first thing we have to talk about is going to be shared resources, and we'll introduce those in just a second. And I'm going to try to motivate you guys to care about congestion, actually, and different ways you can actually proxy the behavior of congestive applications and how they impact data science apps. I'll introduce some experiments, show you some results, and give you some conclusions here. So to start off, a multi-user system. I think everybody's probably familiar with these kind of environments, but I'm not sure. I mean, how many people have actually used like AWS or Google Cloud for data science work? Okay, so there's like, yeah, a handful of people. So how about clusters? I mean, do you guys use clusters in your academic work, or supercomputers, lab computers? So yeah, that's encouraging. Okay, so in these environments, you're essentially sharing something like a server, or you're sharing the network bandwidth, or a distributed file system with other users. And the impact that these other users, you're not supposed to impact other users, but in actuality you do, because they're very complicated systems, especially these big machines, with lots of connected servers and lots of shared resources. So examples of shared resources, things like distributed file systems, right? Network bandwidth, and server CPU cores, GPUs, and also just memory on a server. Okay, so for motivation, I'll introduce this concept of in terms of canaries and congestors, okay? And so a canary is essentially an application that has some sort of communication component. So imagine your application, be it like k-means or a principal component analysis or something that you're doing in your Google Cloud instance, and you want to utilize more than one of the servers to speed up the time it takes to do whatever job you're doing, right? If you have an application with a communication component, at some scale, as you scale it out over many, many servers, you will become communication limited. And when that occurs, you essentially are hypersensitive to congestion. So if there's other messages that are being pushed onto the network, the network cables are finite, so you can only fit so much data down the pipes at a time. And essentially, you feel this as latency, or like an application failing to be responsive as you interact with it. And so a congestor is sort of the opposite of this. It's an application that can theoretically put so much data onto the network that it makes other applications unable to get their data down the pipe, or it introduces packets which maybe are so large that all of the other packets get kind of packed up behind it. And you end up feeling this, in terms of as a impact on your overall performance, maybe variability from run to run on any given day. And so we are specifically interested in data parallel training of neural nets, because this is sort of an emerging workload. Cray is specifically interested in it because we've seen it cause congestion on lab computers, sort of anecdotally, as people are running large distributed training jobs. Other users can feel that in their workloads, and they shouldn't be able to. And so they've put a lot of money and resources into actually solving this problem because of how common it is. So these commonplace symptoms that I'm talking about, I can't really see the screen well. So this graph on the right is essentially showing a histogram of the packet latency it's binning up all of the different packets and how long each packet took as it traveled down the network. So say your application has to send data to some other to another server, as you're doing your distributed application. On a totally quiet system, you'll get 1 performance. That's the curve on the far left, the dark blue curve. When you go and run that same application on a busy network, on a busy multi-user system, you can see the peaks in that latency diagram spread out, and the farthest to the right packets are what you wait for to actually get the application to respond. So that's when you feel like your application completed whatever transfers it was, if you're latency sensitive. Other symptoms of this are corrupt data, hanging nodes or hanging servers, run-to-run variability, where you get different performance one day and maybe better performance the day before. So we use this new benchmark that's been designed by some of the national labs, and they proposed this congestion impact feature, it's a figure of merit. And it's essentially the latency of an application running on a congested system over the latency of the app running on isolated system. So that's basically our canaries and our congester, the time it takes for the longest packets to get in. So here's an example of how you run this benchmark. So you essentially take, if you have an entire system available to you, you take 80% of the system and you leave it quiet. And you let just your test run on only 20% of the system. Okay, so this little diagram on the right here is showing you, a quiet system with a subset of the servers that are available running your canary tests. And then you run the second test, and the second test is the congestive workload. In this case, it's distributed training, and you run that across 80% of the system while you have your sensitive codes run on the same 20%. And you do this test multiple times so that you can get sort of statistics on the system, and it lets you actually get real information about the network hardware and how the network hardware is able to handle workloads running in a congested environment. So we proposed the method to proxy a distributed training of ResNet 50. That's our congester in this case. It does what's called a large message all reduce. As you do distributed training, you essentially need to share gradients across all of the workers. You split up the data set and feed different components to each one of the workers. And essentially, after you have broken up the data set across all of the workers, they all compute their gradients in parallel and then synchronize and use the global aggregate gradients to update their weights. Our canary is essentially the standard latency-sensitive communication kernels used by GPCnet. Other ones are possible, and so GPCnet is really cool, actually, because you can do sort of rapid prototyping of different communication algorithms. You can play around with congesters versus canaries. You can add your own canaries. You can add your own congesters. And so that's all that we did, was we took this and we added our own congester. But you can theoretically add your own canaries and do, explore other communication patterns, or if you know a specific communication pattern that you're interested in, you can use this benchmark and it will tell you about how it responds to congestive hardware, how it responds to congestion on the network. So we set up these two experiments. We essentially wanted to create a situation where we could see whether there was a greater impact if you were filling the system with a single distributed training job. So I'm just training one model on one big data set on the entire system. And then, our second experiment is running multiple small-scale distributed training jobs. So we subdivided that 80% into different numbers of jobs running the same algorithm, right? And so the first use case, I think I kind of described it as a user wanting just to speed up the training of a single neural net. The second use case is something more like a hyperparameter optimization where you have a large data set and a lot of workers are all being used to look across the hyperparameter space and find a good set of hyperparameters to train the model. And we ran this on 2 different generations of Cray supercomputers. So Cray XC was, before I was there in 2012. It's the Aries interconnect, it's called, and the Shasta supercomputer, which is kind of like their up and coming new computer, but it has the Slingshot interconnect, which essentially has this built-in congestion management feature. So here's our random ring sensitivity test, but essentially the sensitivity tests, there's 2 of them, and you'll see the same graph here on both slides. Essentially, the results are that on the older interconnect, there's a huge impact from running distributed training on the canary test. And so you see a factor of like 12 when you're using 1DL proxy, and up to like 16 when you're running up to 8. And it's not like, going up to 16 doesn't necessarily cause the congestion to increase linearly. So the next slide here, we show multiple all-reduce tests. So same thing, it tells you about how distributed training jobs can actually interact with each other. So other distributed training jobs could be running alongside these, and this is kind of telling you what the impact is there, but it basically looks the same as before, and right, so that yellow line with the yellow boxes is the no impact at 1, right? Like that's what it should be if there was no impact at all. Okay, so our conclusions are that emerging workloads have a significant impact on the applications that you guys are using. I don't know if you guys are using k-means specifically in the cloud, on your cloud services, or if you're doing PCA, or what exactly the algorithms are of choice. But the point is, if they have a communication component, they will become sensitive to congestion at some scale. And your options for dealing with congestion are essentially to like kind of latency sensitivity prove your code, so you can like dive deep into the code and change the algorithm, the underlying communication and computation algorithm. And if you don't want to do that, you can just not share, and you can actually just dedicate a portion of the wire connecting servers and connecting the I/O subsystem, and dedicate that to every user, and then you underutilize your network. You can over-provision, so the people that own the computer can just buy more network, and they can just plug as many wires as they can into the thing. Or you can choose a next-generation interconnect with congestion control. And this actually seems to have a pretty significant impact on these workloads. And then, yeah, one final plug for GPCnet, because we found this benchmark was really useful in doing this kind of work. All right. And we have a booth here, too, so come visit us.